So number 11 here, if you remember from like last Thursday, that was a while ago, we are solving trigonometric equations. So what type of equations do we solve? Yes, what kind? No. Scroll to the top of your notes. If you don't know an answer to a question, at least you know where to go to look for the answer. What type of equations do we solve? Conditional equations, right? Yeah, that's what we're doing. We're solving conditional equations. So the conditions are essentially the values of the independent variable that when you plug them in, make the equations true. And we've already gone through kind of a gamut of ways to find solutions to trig equations. It's a combination of, again, trigonometric identities and or algebraic sequences. So our goal, remember, is to get a single trig expression or function by itself. And if we have more than one term, like we did up here on example 9, that have variables in them and they're unlike terms, then we get everything on one side and set it equal to 0. And then we factor, and that allows us to split it up into two smaller equations. Let's see. On example 11 then, on part A, we have 2 sine of x plus the square root of 3 equals 0. In this case, it's already equal to 0. Is that our goal? Is that what we wanted to do here? Not in this case. Why? Yeah, there's only one term here that has a variable in it. So whenever you have a single term with a variable expression, you actually don't want to get it equal to 0. You want to isolate that variable part. Okay, so we want to get sine of x by itself. So what we would do is we'll subtract the square root of 3, and we get this, and we divide through by 2. So we get negative square root of 3 over 2. Now, if this were just 2x plus the square root of 3, instead of sine of x, we'd be done. We'd have x equals this number. But here's where the fun begins, right? Trigonometry. So now we have sine of x equals negative square root of 3 halves. It's unit circle time. And we are not going to be taking the inverse sine function of both sides to solve for x, but rather the inverse sine operation. So it says up here to solve each of the following in our happy zone, right? 0 to 2 pi. That's once around the unit circle. So 0 is included and all the way around up to but not including 2 pi. So now we just think, okay, where on the unit circle, for what angles x is sine equal to negative square root of 3 halves? 4 pi thirds and 5 pi thirds. Very good. And those are your two answers. If I had wanted it from 0 to 4 pi, I would take those two, keep them, and then also do what to get the next two? Add 2 pi. Right. Good. If I wanted all the solutions, then I would take each of these and add what after them? Plus 2 pi n. Good. That's what we talked about last Thursday. All right, so again, to review, a single variable term, get it by itself, okay, not equal to 0. All right, letter B, 4 secant squared of x equals 8. Do I want to bring the 8 across? Well, sometimes if you set it equal to 0 with the single trig function, it might work, but in this case, we can't factor that. If you did bring the 8 across, you might be able to factor it as a difference of squares. But in general, again, if you just have a single term with a single variable in it, you want to isolate that term rather than set it equal to 0. So in this case, it's easier to divide through by 4, and 8/4, of course, is 2. Now I need to get the secant of x by itself. So we're peeling back the layers. How do you unsquare something? Square root of it, right? So the square root of the left side gives us secant of x. And on the numeric side, when we take the square root, we have to remember and not to forget to do what? Plus or minus. Yeah, and if you forget the plus or minus, you're going to lose potentially half of your solutions. Okay, so now we just need to think where secant is equal to the square root of 2. And if you don't like to solve a secant problem, or if you don't like to solve a cosecant problem, or you don't like to solve a cotangent problem, you can always turn it into a cosine, sine, or tangent problem pretty easily. Because if the secant ratio is the square root of 2 over 1, then what would the, bless you, cosine ratio be? Yeah, 1 over the square root of 2, just the reciprocal of that, which when you rationalize it, of course, is what you said, square root of 2 over 2. So that works great if you have secant cosecant, or cotangent equal to something. Flip both sides, put it in terms of a sine, cosine, or tangent, which is a little bit easier for us. All right, so now from the unit circle within one rotation, where's the cosine equal to either positive or negative square root of 2 over 2? Pi fourths, 3 pi fourths, 5 pi fourths, 7 pi fourths. Very good. It would be every single one of the 45-degree reference angles, all your pi fourths reference angles. Positive in 1 and 4 and negative in 2 and 3. All right, so far so good? Nothing to it, kind of fun, using the unit circle in reverse. All right, letter C. It's equal to 0. Is that what I want? Very good. Again, I have a single trig term. There's not two terms with variables, so I want to isolate the cosine squared so I can isolate the cosine. So if I bring the 3 over and divide it by 4, hopefully you can go straight to 3/4. Positive 3 over 4. And now when you take the square root of both sides, you get cosine of x on the left, but on the numeric side, again, you take plus or minus. And because it's a quotient, remember the square root of a quotient is the quotient of the square roots. So let's take the square root of the top and bottom individually. We get the square root of 3 over the square root of 4. And the square root of 4 is 2. Yeah. So if it's a trig equation and you don't have a calculator to solve it, it's going to be a ratio that shows up from the unit circle. So if you're not getting a unit circle ratio there, your algebra is incorrect. All right, so now it should be pretty easy. We're looking for all of the angles x between 0 and 2 pi, where the cosine, the x-coordinate, essentially, is plus or minus square root of 3/2. So what's the first one in quadrant 1? Pi 6, and in quadrant 2? Well, let's do that. Yeah, sure, 11 pi 6. Those are going to be the two where it's positive, right? Quadrant 1 and 4? Oh, that's fine. And then if you want to get the two that are negative, 5 pi 6 and 7 pi 6. Yeah, so you don't necessarily have to list them in any kind of order, as long as you get them all in there. So if you want to mentally say positive and then negative, or if you just want to think about I'm rotating all the way around, I'll list them as I rotate. She emailed me, you're good. Yeah. Okay. Those, I guess, were the easy ones. One single trig expression, isolate it, solve for that trig expression. Now on D, what do you notice? You have 2, right? So if there's 2, now somehow you need to either get it equal to 0 and factor, or somehow get it into a single trig function. So anybody have any idea on what we could do here? There's lots of ways to go about doing this one. The cofunction? Oh, yeah. Let's think about that. The sine and cosine are cofunctions of each other. So you can write sine of x as cosine of pi halves minus x, or cosine of x as sine of pi halves minus x. But the rules of solving the equation are going to be kind of the same as they are for proofs. Your number one priority is to try to get the angles the same. And right now, both of my angles are already the same. They're both x. So if I change one of them to pi halves minus x, even though they might both be in terms of the same trig function, it's kind of the wrong direction because now my angles are different. You could, like which one? That was, she was recommending a cofunction identity, but that's not quite going to work because the angles get changed. We can use any of the PIDs here, right? Because they're not squared. Can you square both sides? If it's a conditional equation, can you square both sides? Yeah. Just like we did over here, we took the square root of both sides. In a conditional equation, you can square both sides. So if you wanted to do that, you could do that. I'll show you several ways to do this one. Sine squared equals cosine squared. I'm going to put a little asterisk here because we've talked about it this year, and of course in Algebra 2 you did as well. When you solve an equation by squaring both sides, you need to make sure at the very end you check for what? Remember? Extraneous solutions. Very good. Yeah. Because you're taking something that's like a degree 1, like a linear function that has one solution, and you're squaring it, and you're making it to a quadratic, which can have up to 2 solutions, and maybe one of them doesn't work. So anytime you square both sides or raise both sides to a higher power, you need to check for extraneous solutions. And now that they're both in terms of sine squared and cosine squared, now we can use a Pythagorean identity. And it doesn't matter which one. Let's do this. Let's change sine squared into cosine squared. So that's 1 minus cosine squared equals cosine squared. And now I can get everything on one side. I'm sorry, I can separate the cosine squareds because it's really the same variable. So if I bring the negative 1 over to the right side, I now have cosine squared plus cosine squared, which is 2 cosine squared. And now it kind of turns into a problem like we saw previously. I'll isolate the cosine squared by dividing through by 2, and I get 1/2. And then I'll take the square root, and I get plus or minus the square root of 1, which is 1, over the square root of 2, which is square root of 2. Which if we then rationalize that, we get the square root of 2 over 2. And now it's kind of deja vu, isn't it? The solutions are pi fourths, 3 pi fourths, 5 pi fourths, and 7 pi fourths. But remember an asterisk. What was the asterisk for up above? Extraneous solutions. So how do we check for extraneous solutions? We ask them, yo, you extraneous? We could, and I just did. And I'm still waiting for a response. How long should we wait, Zane? What? Until the end of the year. Huh. No, let's try them out. We got to plug them back into the very, very original. Okay? And we look for the sine equaling cosine. If you plug in a pi fourth, sine of pi fourth, cosine of pi fourth, both square root of 2 over 2. So that's good. What about 3 pi fourths? Same, exact same. Sine of 3 pi fourths is positive square root of 2 over 2. Cosine of 3 pi fourths is negative. So they're opposite. So 3 pi fourths is extraneous. So we'll just draw a line through them, 2 lines actually. And which other one's extraneous? 7 pi fourths, right. So in the quadrants where x and y are opposite signs, namely quadrant 2 and 4, they're extraneous. So the only 2 solutions then are pi fourths and 5 pi fourths. That's a lot faster than waiting for them to respond. So you could have done the exact same thing, and you could have written them in terms of sine squared, and you would have had really the same problem, or the same type of strategy for solving. So that's one way to do it. Let's kind of shrink that one down. Another way to do it is just by guess and check. You could have said, oh, for what angles are the sine and cosine values the same? It's going to be at your pi fourths, where they're both positive, and 5 pi fourths, where they're both negative. So that's a legal way to do it. But there's another way to do it that doesn't involve extraneous solutions. What if I divide both sides by cosine of x? Is that legal? It is, as long as I don't lose information, right? Like if there was a cosine of x on both sides and now it would divide it out, I would lose information. But it divides out on this side to give me a 1, but it doesn't divide out on the left, does it? It's still there in some capacity. It's still sine divided by cosine. They don't divide out. What is sine over cosine? It is tangent. And now I have the same equation, tangent of x equaling 1, where on the unit circle is tangent equal to positive 1? Well, at pi fourths and 5 pi fourths. Good. Tangent is equal to positive 1 only when the x and y's on the unit circle are exactly the same. So that's another way to do it without having to check for extraneous solutions. So you'll find that the methods kind of vary, but it's a combination of algebra and trig identities. I kind of like that method. All right, letter E. 2 cosine squared of x equals cosine of x. Should I just divide both sides by cosine? Not in this case, because I will lose it on both sides. I will be losing the cosine from both sides. It'll divide out. It's not going to still be there residually. So what should I do? Subtract cosine. Yeah. I have 2 terms, and they're different because one's squared and one's not. It's like having an x squared and an x. They're different terms. They're unlike terms. So whenever you have more than one term with a variable in it and they're unlike, that's when you want to get it equal to 0. And of course, once you have something equal to 0, then your goal is to factor it. And your first rule of factoring is? Yeah, look for the common factor, the greatest common factor. In this case, it's a cosine factor. So in the first term, we're left with a 2 cosine of x minus in the second term, when you divide a cosine out from a cosine, you get a 1. And remember, it's important to keep it equal to 0 as you work down. It has to maintain it an equation. And now the zero product property allows us to set each of them equal to 0. So this kind of breaks it down into what appears to be twice as much work, 2 equations to solve now instead of 1, but they're both 4 times easier, so it's really half as much work. Do the math on that. All right, so now from the unit circle, where is cosine equal to 0? That's where it's cosine of 0 is 1, cosine of pi is negative 1. Pi halves and 3 pi halves. Yeah, good. And over here, this is kind of like what we started with. In this equation now, I have a single trig function. So I want to isolate the cosine. So you get cosine of x equals positive 1/2. And where is cosine equal to positive 1/2? Pi thirds, good. Know thy unit circle. 5 pi thirds. Excellent. Know the unit circle and know yourself. I think Buddha said that. So 4 solutions there between 0 and 2 pi. Do we have to check to see if any are extraneous? Yeah, we don't have to. We didn't square anything. As long as our math is right and we know the unit circle, they should work. All right, and that brings us to the last one here. Letter F, 2 plus 2 cosine of x equals sine squared of x. Yeah, very good. Yeah, if you want to get it on the other side first, that would be a good first step. Notice the angles are the same. You got an x and an x, so that's good. Later on in the next section, we're going to learn, or in 2 sections from now, we're going to learn identities for dealing with the angles when they're not the same. But right now, the angles are the same, but I have 2 terms then that are unlike, and they both have variables. So get everything on one side and set it equal to 0. So that could be your first step if you want to take it one step at a time. And then you look for a common factor. There is no common factor other than 1 or negative 1. It looks kind of like a quadratic trinomial, right? You have a squared term, a non-squared term, and a constant. But what do you notice? Your functions are different. It's like an x squared and a y. They need to both be like x's. So what I need to do now is put the entire problem either in terms of cosine or sine. It doesn't matter which one. But if they're both in terms of sine or both in terms of cosine, I might be able to factor it. So what are your options? Well, look at the cosine. Is it easy to turn a regular cosine into a regular sine without changing the angle? No. But what about sine squared, as you already saw? Sine squared is easy to turn into cosine squared, a la Papa Pid. There you go. So I'm going to put parentheses around it, which I highly recommend when you're doing any kind of identity replacement, especially when there's something out front that's not a single plus 1. So here we go. We got a 2 plus 2 cosine of x minus parentheses. What is sine squared equal to? 1 minus cosine squared. Good. And now what I'm going to do is I'm going to distribute, expand everything out, carefully taking one line for each step so I don't make a careless mistake. Minus 1 plus cosine squared. So now I still have 2 variable terms. They're unlike, squared and non-squared, but they are both in terms of cosine, which is fantastic. So if we write it in descending order, we got a cosine squared first, and then I got a plus 2 cosine of x, and then I have a couple of constants that I can combine. A 2 minus 1 is a plus 1, and it's still equal to 0. And now, as we saw last Thursday, squared term, non-squared term constant, that could factor in to the product of 2 binomials in terms of cosine. So this would be the easy one because cosine squared is really going to just factor into cosine of x, and that goes in the first slot, right? FOIL, first, outer, inner, last. The first is cosine times cosine. And look at the last one here, plus 1. 1 is prime, and it only has a factor of 1 and 1. So that's pretty easy. And then the middle sign is positive, so both of these have to be positive. So really, if you notice, this was a perfect square trinomial. It factors into a binomial squared, cosine of x plus 1 quantity squared. You don't have to write it as cosine of x plus 1 quantity squared. You could just set one of them equal to 0. That's fine. You don't have to set both of them equal to 0. You could, but you're going to get the same answer. And you don't have to repeat it twice. You don't have to repeat it twice. Okay, so now what? Subtract 1. Isolate. We have a single trig function. Isolate it. Cosine of x is equal to -1. And now from the unit circle, where is the cosine equal to -1? Pi. So x equals pi. And that's the only solution between 0 and 2 pi. Sweet. Let's plug that one in and make sure it works. Plug it back into the top. We got a 2 plus 2 cosine of pi. What's cosine of pi? -1. So we get 2 plus -2, which is 0 on the left. And over here, remember, if it's sine squared of x, we're actually going to be plugging in a pi to get sine of pi, which is what? Sine of pi? 0, and then you square the ratio. 0 squared is 0. Yeah. That's important to remember, that sine squared of x is equal to sine of x, the ratio squared. And if you wrote it like this, sine of x squared on your paper, guess what? You're going to get it wrong, because that's squaring the angle, not the ratio. All right, so that's it. They're going to be a lot more fun as we learn more and more identities. But right now, just using the fundamental identities, this is kind of the nice variety pack of types of equations you should be able to do. Perfect timing. We just, came back. Weird. A new version of something is available. Well, that's it for today. So I know that we kind of took it easy last week, but today we could take it easy as well. You have the rest of the class period to do those 4 problems, and you could do them on separate paper and just turn it in. It's due tomorrow in class. We'll probably quiz tomorrow as well, or some of these